This is for a problem set. This is a picture from page 1. Here we go. Page 123. This is about electrolytic properties. One of the ways that you can tell if a solution has ions, has a lot of ions, very few ions, or no ions at all, would be to use an apparatus that looks like this. Now you can see the light bulb. We have a power source, like you literally plug it into the wall, and then the wall power comes in through here, and then if this here has ions, if that solution has ions in it, that means it conducts electricity. The electrons move through the solution much easier and complete the circuit here to give us power there. If there's only a couple of ions, not nearly as much as like if you put salt in water would light the bulb up very well. But if we have like something like a weak acid, that would be something that ionizes at a very low percentage, like 1 or 2%. And then you notice that it's tough to see it, but the light bulb wouldn't be quite or nearly as bright. And then if you throw sugar in water, sugar is an organic compound and does not have ions per se, then you would get nothing from the light bulb. It would not complete the circuit. Or if you had pure water, it would be the same. Everybody thinks water's a great conductor. Actually, it's not that great, not compared to salt water. Salt water is much better at conducting. So let's take a look. So it says, number 4, a 0.1 molar solution of acetic acid causes the light bulb in the apparatus of figure 4.3, which is what I just showed you, to glow about as brightly as a 0.001 molar solution of HBr. Now, how do you account for this fact? Well, we have two things here. We have acetic acid and we have hydrobromic acid. Okay, so here we have a weak acid, and the weak acid has a concentration of 0.1. Okay, this is the number of moles per liter. Okay, that's what that means. That capital M for molar means that there's 0.1 moles per 1 liter, okay, which is actually a reasonably strong concentration. But notice that my strong acid, because HBr is one of the strong acids, has a concentration 100 times less than my weak acid. That means that the ionization happens 100% of the time here for the HBr, okay, that means that this happens then about 1% or 100 times less. So just to give you an idea of what the weak acid would look like, HC2H3O2 changes to H plus C2H3O2, the minus 1. This breaks apart only 1% of the time. It's actually closer to 1.7, I believe. But notice that when this happens under normal circumstances, that means that I still have, there's only 1.7% of this in the solution and 1.7% of this in the solution, and over here I have 98.3% is still left looking like this. Whereas if I have a strong acid of HBr, I get a plus and Br minus like this. That means 100% of the solution is H plus and Br minus, and there is nothing left over here. The HBr is not represented at all, like it's completely broken up. So that's the difference between a weak acid and a strong acid. Okay, now why did I tell you all of that? Well, it makes sense that when we put the solutions in that apparatus that shows you how many ions there are, by looking at how bright the light bulb is, it says it glows about as brightly as a solution 100 times less concentrated. So that means, how do you account for this fact? That means that we have a lot less, use a different color here, a lot less of the ions being produced compared to 100% of the strong acid. Okay, that's how we account for this. The weak acid with a 100 times higher concentration produces about the same number of ions as 100 times less concentration of a strong acid that that breaks apart 100% of the time. Okay, so what you have in strength of concentration for the weak acid is then decreased by the number of ions that are produced from the weak acid. What you have lacking in the concentration of strong acid actually produces 100% ions. So, okay, I'm not sure how else to say that. Let's keep going. So the labels have fallen off two bottles, one containing MgNO2 and the other containing PbNO3. You have a bottle of dilute H2SO4. How could you use it to test a portion of each solution to identify which solution is which? Well, let's go through. Let's do the MgNO3 plus H2SO4 like this over here. And then, PbNO3 plus H2SO4 like this. Okay, so here this is, of course, a double displacement reaction, which means over here I'll get AD and CB, which means Mg with a +2, SO4 with a -2 plus, and then we have H with a plus and NO3 with a minus, like that. Okay, I don't even need to balance this or do anything other than just list what compounds I get on the other side. Let's do the same thing. That's A, B, C, and D. So that's going to be AD here, which is PB plus 2, SO4 minus 2 plus, and then H again, NO3 minus, like that. So I take a look. Notice these two are the same, so they don't matter. But these two are not the same. So when I check on my test equation, my equation test sheet for the solubilities of those two products, I take a look at magnesium. I go all the way across the sulfate, which is the third last one. It looks like magnesium says AQ, which means it dissolves in water, but PB with a +2 is a solid. So if you get a solid here, you've just identified which one is the lead. So you know which is which. All right, I'm on a roll. Let's keep going. Which of the three solutions is shown in the schematically to the right corresponds to the results of each of the following reactions? Water molecules are excluded for clarity. Okay, so let's go through this. So I'm matching A, B, and C with 1, 2, and 3. I, and I. Let's see. So number 1 has only things dissolved in the water. Okay, so that means that there's stuff dissolved in the water, but no solids, because these are evenly spaced, and solids would look more like number 2 here. So this is only aqueous, right? Only aqueous stuff. And I take a look over here, I see solid and water, I see aqueous and water, and I see solid and aqueous. So which one is number 1? I would definitely say that this is definitely B, because there's no solid as a product for letter B. Okay, so this is B here. Likewise, notice I have stuff dissolved and still also a solid. So here's my dissolved stuff, and then here's my solid. So that means that number 2 is letter C. And then, of course, we have just the solid here and water, which means that this is definitely number 3 is letter A. Okay, so that makes sense. Good. Let's keep moving. Write the balanced dynamic equation for the reactions that occur each. Okay, so this is a double displacement reaction. You're going to get sick of doing these, but it makes you, a better person. So over here I have A and D, Cr with a +3, like that. D is CO3, and we know that that's I'm minus 2. So I'll crisscross in a second, but over here I have NH4 as my C, and B is SO4, that's a plus 1, and SO4 with a minus 2, like that, is a D. Okay, so I go back through now, and I crisscross, and that's going to get me parentheses and a 3 here, and a 2 here, and this one's going to be parentheses and a 2 here, and then I can get rid of all of the charges. Now that is my equation. Let's go back through and make sure that we are balanced. So now I have a CO3 with 3 on the outside. Here I have CO3 with just 1 on the outside. So that means I need a 3 here. Usually I start on the left. Okay, let's start on the left-hand side because that's going to screw everything up. So I got 3 here. I don't know why I erased that. But I have 2 and 2, so that's balanced for CR. So I have 2 and 2, so that's balanced. I have 3 SO3s here, and I only have 1 SO3 over here because there's no parentheses and numbers on the outside, so I put a 3 there. Now that balances my number of SO3s. Now I have 6 NH4s because 3 times 2 is 6, and here I have 3 times 2 is 6. So that's balanced, 1, 3, 1, 3. Good. Now let's go through and write down, this is the long part. I'm going to go through and write out all of the ions, and this is going to take a little bit. So hang with me. Anywhere that says AQ, I'm going to separate them into ions. Poop. Okay, on the other side here. Now, so what I need to do is I need to check CR2, CO3 looks like, okay, what's CR with a plus 2, and where's carbonate? Carbonate's right here. That's a solid. This right here is a solid, so that makes this stay the same, like that, and then so which ones are the same on both sides? I'll give you a hint. It's the ones not in the solid, which means I can get rid of the 6 NH3 like that and the SO4 like that. So that means I have 2 CR with a plus 3 plus 3 CO3 with a minus 2. That's a 2. And then CR2, CO3, 3, solid. There it is. Okay, I'm going to let you guys finish this out. There's nothing different. The last 2, B and C, you will need to do completely, just like I did, to get full credit for 4A problems, but it works exactly the same as letter A. Exactly the same. You're going to need the test, the equation test sheet, and you're also going to need a periodic table of ions. Okay, good luck.